Hi everybody, this is Gigi from Kauai Community College. In this video, we will attempt to do some modeling with mathematics, okay? Now, that really doesn't mean you're gonna be putting on dresses and start walking around like you're modeling, but what modeling with mathematics means is just basically making sense of real life situations using mathematical models, okay? Now, in this video, we will talk about a linear model and an exponential model. And we're going to compare and contrast the two. Those are the two popular models that we can use that would model many of the situations that we encounter in real life. All right, so let's get started. All right, linear versus exponential. So let's consider this scenario. You're printing t-shirts, okay? And this shop, the custom tee shop, charges $10 a shirt, plus $150 for a setup fee. That's just a one-time setup fee. Okay, so let's model the situation using a graph. Okay, so you've seen this before, right? Now, let's say this $150. What does that mean? One-time setup fee. Well, it means that even if I don't print a shirt at all before I even start thinking about printing shirt, I need to pay $150 for them to set up the plates. Okay, so that give you a dot right there. Zero shirt, 150 bucks right away. Okay, and then they will charge $10 per shirt. So how am I gonna model that using this graph? Well, let's say we are going to print, say, 10 shirts. Okay, so 10 shirts, $10 a shirt, that's $100 plus the $150 I had to pay in the first place. So now we are at $250. So I have 10 shirts, $250, right? Now suppose, say, I print not 20, but say 30 shirts. Okay, so 30 shirts, $10 a shirt. That's 300 plus 150. I have 450. So I have 30, 450. That's the dot there. What if we print 45 shirts? Well, you've got it. That's $450 plus 150. So we are now at 600. Now, if you think about the trend line for this graph, it's going to look like a straight line, right? And let's take a look at what make a straight line a straight line. Okay, what make a line a line? Well, let's say we are looking at the rate of change from one place to another. Say from 0 to 10, this would be what? The change here is 100, right? And the change here is 10 shirt. So I would have 100 over 10, and that is 10. And where did we see that 10 before? Okay, now suppose we go from this dot to that dot, which is a lot further away. What's that rate of change? Well, the change from 250 to 450 is 200. The change from 10 shirts to 30 shirts is 20 shirts. So that rate of change is 200 divided by 20, which is still 10. And where have we seen that 10 before? Okay. What about this right here? That's 150 over 15, which also give you the rate of change is 10. Now, where's that 10 coming from? You're right, that's the $10 per shirt. Yeah. Now, and this rate of change is a constant rate of change. So we will define what we call a linear growth model, and that has a constant rate of change. In this case, $10 a shirt. Okay, now we also see that, and we're going to define that constant rate of change. I'm going to use the letter M for this constant rate of change equals to 10. Okay, and then we know that we started out with an initial value right here of 150. So I'm going to define that as, I'm going to use the letter B for that initial value. Okay, and that would be 150. Now, what equation will model that? Okay, think about how we calculate the cost of the shirt. It would be the cost of the shirt is 150 plus $10 multiplied by however many shirts, right? So we're also going to define the X as the number of shirts and the Y as the cost in dollars. So X is on the X-axis, down on the horizontal axis, and Y is on the vertical axis, and that would be considered as the cost. So what's the relationship between X and Y? We would say Y is equal to B, the initial value, plus the rate of change, that constant rate of change multiplied by X. Okay, and that is a linear model in math. And what makes it linear? The constant rate of change. Okay, so that's important. As soon as you say constant rate of change, that's a linear growth model. Okay, now consider this scenario, the magic penny. Okay, so one lucky day, you were hiking in the forest and you rescued a leprechaun who was caught in a bunch of branches, right? And he gave you, he hands you a penny and said it will bring you fantastic wealth. Okay, now you go home, you place the penny under your pillow, hoping something magical gonna happen because he did promise you wealth, right? So, okay, I'm not very good at telling stories, as you can see, but here's the underlying part of the story. The leprechaun gave you a magic penny. So while you were sleeping at night, each magic penny turns into 2 magic pennies. How do we model that scenario? Okay, let's think about that for a second. At the beginning, you have 1 penny. Then you went to sleep. The next day, you have 2 pennies. And then if you just kept them under your pillow because you want to find out if the pennies are going to grow some more, right? Oh, each one of those pennies will turn into 2 more magic pennies. So now you have 4. After the 3rd day, you'll have 8. And then after the 4th day, you will have 16. It's off the chart, literally. Okay, now if we follow this trend line, and actually it's not a line, it's a curve, right? So what's the difference between this scenario and the previous linear model? Well, the rate of change, if you take a look from here to here, is not the same as from here to there, and definitely not the same as here to here. Okay, and as a matter of fact, this last change right here that I'm drawing is huge comparing to the previous rate of change, right? So this has a changing rate of change, but it still is changing relative to the fact that each magic penny turns into 2 magic pennies. So let's take a look at the numbers and see if we can see some kind of pattern. We know it's not this, the change is not the same every time, so we're not adding the same amount every time. Now, what are we doing here if we just look at the pattern? Well, we can see that this is being multiplied by 2. So you see how to go from one day to the next, it's being multiplied by 2. Well, why? Because of this information right here. Each magic penny turns into 2 magic pennies. So we're multiplying by 2, right? We're doubling every time. So we're not adding the same amount every time as a linear model. What are we doing here? Multiplying by 2. And this is what we define. This is an example of an exponential growth model. And what is an exponential growth model? It has changing rates of change relative to a multiplier. In this case, the multiplier is 2, and I'm going to use the capital letter M as my multiplier, okay, as opposed to the constant rate of change is a small m that I used before in the linear model, okay. Multiplier in this case is 2. And then my initial value in this case is 1 penny, and I'm going to use a capital B as my initial value in exponential growth model. And as we can see here, X, let's call X being the number of days and Y being how many pennies that there are in underneath my pillow, right? And soon enough, there's going to be a pile under my pillow and I can't sleep under there. but anyways, what's the equation for this? We would say that Y, which is the number of pennies, is equal to B, the initial value, multiplied by M to the X power. Because you see here, it's being multiplied by 2, 2, 2, and 2 again. And repeated multiplication we know is exponent. So that is why we have the multiplier to the X power. Okay, how many days it's been. Okay, so that's the definition of what a linear and an exponential growth model is. Let's see if we can distinguish between the two. Okay, linear or exponential. Oopsie, peekaboo, you saw that word. You didn't, pretend like you didn't. Okay, so the number of students at your local high school increases at 50 students per year. For the past 4 years, how many students are there now when the population 4 years ago was 750? Well, when you read this, you would say, well, what's the rate of change? That would be 50 students each year. So this is a constant rate of change, and that calls for a linear model, where M, that constant rate of change, is 50. Okay, and the initial value here is 750. And the linear model said Y is equal to B plus MX. So I would have 750 plus 50 times 4, because it's been 4 years. And we would say now there are 950 students. Okay, so what makes it a linear model? Constant rate of change. All right, next example. Let's see here. The price of milk has increased by 5% per year, and the price of a gallon of milk is $4 5 years ago. Then what is the price now? Well, 5% per year. That calls for a changing rate of change. And it's relative to the 5% increase. Okay, so what 5% per year mean after 1 year is 5% of 4 in addition to the $4, right? And then the year number 2, it would be 5% of that, I would say 105% because it had increased by 5%, right? So every time you would be multiplying by 105%. That means it is an exponential model and the multiplier is 1.05, right? 100% original plus the 5% additional, 105%. As a decimal is 1.05, okay? And the initial value is $4. The exponential model say y equals b times m to the x power. So 4 times 1.05 to the 5th power. You would put that into your calculator and you would have $5.11. Okay, now let's bring ourselves to this current event here. COVID-19 scenario. Linear or exponential? And that's for you to go look up and discuss with your family. All right, that's it for me today, and I will see you next time.